Yes, first I would like to thank you sincerely for taking care of us, for science, of course, but not only. Okay, so you see that I'm a sort of a guy in between a C, in the sense that I'm a photonic guy. And so probably I will say stupid things in fluid dynamics, but that's the game, I mean. And so I will try to try to explain you how we can use optics. In fact, I want to rehabilitate optics after our discussion of yesterday of acoustics. In fact, I love the two. But in order to see how we can manage things at small scales, and particularly if we can go to rheology at small scales, because one of the tricks, no, I should do that, yes. No, there, here, is that, of course, I will not make a revolution in, I will not make a revolution on rheology. I'm not a rheologist. But what we know is that, of course, we use rheometer and so on, but these systems mainly fail when we have very tiny systems. I'm thinking typically of biological liquids, and when we want to work in confinement with very small quantities, and when we are looking for out equilibrium situation. And one of the examples that interests me a lot is this one. That is, when you look the drying of paint and inks, when you look at paint, it is wonderful. It is clear, and you have solvent evaporation and so on. And you have a huge amount of technology, engineer technology, because we know that drying a drop of ink is just something absolutely complex, in the sense that the solvent evaporation modifies the concentration, the rheology, and the final deposit. I will give you an example in my conclusion, but you may have this coffee ring effect. So it's just a very complex system with just a drop here on your table. And so the question is, I would be interested to analyze the rheology of such a system. And we know that the rheology of such a system, which evolves continuously, is not accessible with classical rheometer. So that's the idea that I will follow. And to do that, I have to go back, because maybe you are not familiar with optics and so on, but in this kind of things. But here are the different techniques to measure the rheology at small scales. And I will detail very fast that. The first one, of course, is using atomic force microscopy, which is a quite nice object, but the problem is often the dissipation here, which is not controlled due to the pinning of the interface. And then, of course, we have this pinning here that may modify things, even if you can get results for that. Of course, it is not always adapted to kinetics. You have a better situation which starts to be contactless in some way when you use two fluids. In this case, of course, close to what you are trying to look, it's okay, it's completely contactless, but you still have this contact pinning of the needle here, but it's very sensitive nonetheless, in some situations. Now, I feel, if I continue to think about sort of contactless or small size investigation, you have an old experiment here. At the very beginning, they try to stretch cells by gluing beads and using optical traps to stretch it. Once again, one of the problems is the control of the gluing, which is not a piece of cake. Another example, which is quite interesting in optics, is to use, particularly if you have drops and so on, is to use anisotropic beads. You have an example, the classical example is vaterite. And then you have to set this bead inside your drop. And since it is birefringent, of course, if you shine with a circular polarized light, then it will turn, and then you will have, from the torque, you will get an idea here you have the example of methanol, of the viscosity of solution, methanol solution. The problem is you have nonetheless a bead, so it has a size. So you need to have objects that, let's say, are slightly larger than that in order to avoid finite size effect. And you always have a problem of the adsorption. That is, okay, methanol is okay, but what happens at the surface of the bead remains an important issue nonetheless. So people tried to go to analyze these effects of rheology using different really contactless methods. One is the first. One of the first is the electrostatic pressure. I wrote electric. So what happens is, of course, if you bring a needle very close to an interface, you will have a gradient of field. If you have your gradient of field, you will have an electrostatic pressure. So you will pull the interface. And so from the pulling, you can get information about its dynamics. One of the problems of this approach is that the field is inversely proportional to the distance. And you are modifying the distance. So it's good, but it's tricky. And the collapse happens 99% of your experiment. So then you have acoustic pressure that works for a long time. You see this paper, I just give you an example. Here the transducer is inside the pool. It is focused on the interface. And what will happen is more or less what I will show you with optics. This is slightly different for the impedance, but roughly speaking, you will deform your interface, and from the dynamic of this deformation and the final shape, you can get your rheological properties. So I will talk about light. So as far as we trust that the momentum of a photon is proportional to the index, which is called the Minkowski formalism, there is a controversy. Well, now it's okay. What happens is that if you start from a dielectric with a large refractive index, incident like that, what happens is that it will lose momentum at the interface. And by conservation, what happens is that you will deform your interface. What is funny is that if you go in the other direction, the same happens in the linear regime, in the sense that the photon will gain momentum and then the deformation will again occur in the same direction, that is towards the optically less dense medium. Light loves refractive index. That's why you have optical trapping, and this is exactly the same thing. And in order to see these kind of things, I can give you, I can go very fast in that, because I don't have that much time. You can have a mechanical point of view, which is very easy. So you count the incident photons which are given to the interface. You remove the photons which are reflected and which are transmitted. And you can calculate the variation of momentum. And from this variation of momentum, you see that you have no tangential effect. Radiation pressure is a normal stress, strictly a normal stress. And you use your Fresnel coefficient, of course, for the energy. You see that it is normal to the interface. It is always directed towards the dielectric of lowest refractive index. This is confirmed by electromagnetism, but if you want to do things well, you have to make the electromagnetic calculation, because you may have the polarization, which is not present here. So you may have some more things. What happens is that you will balance the radiation pressure with buoyancy and Laplace pressure. I will write Laplace pressure in this way for the concerning the talk we had before. So you can write that like that, and here you have the beam intensity. Usually it's the power divided by the omega 0 is the beam, so-called beam waste. And you have this exponential here. What is interesting is that from these two terms, you can define an optical bond number. where the length scale becomes the waist of the beam, so it's a sort of virtual particle here. And you can get easily the height of the deformation in stationary condition, as well as direct expression of the height at the beam center. I will not have time to go inside how to calculate the dynamics, but you have two fluids, so you solve the Stokes equation in both sides. You have to take into account the electromagnetic Maxwell stress tensor at the interface. And you get this expression, which of course involves a bond number, but that shows you that you have a sort of exponential growth like that. It is not radically exponential. And you have two time scale, but you know that in fluid dynamics. That is, if you have thick films, you have a time scale which is just related to the capillary velocity and the size of your excitation to the waist. And you know, for thin films, of course, you will have an interaction which leads you to an extra term in the dispersion relation, which is in h cubed here. And so, if you look also at the relaxation, you will have the same time scale. So this is typically the type of signal we will get. That is, this is from glycerol. You shine your laser, you have your deformation increasing like that, and when you turn off the laser, you have this relaxation. And what is interesting in this is that I have to do that, is that this value here in stationary condition will give you in some way the surface tension. And of course the dynamic, if you have the surface tension, you will get the viscosity. And now I agree with Michael. The problem is order of magnitudes with photons. That is, at normal incidence, you can have a very simple order of magnitude of the radiation pressure, of the curvature. So you can get an order of magnitude of the height of the deformation. And you see that for normal fluids, you are in between 10 and 100 nanometers. I will show you tomorrow what happens when, instead of having this surface tension here, what we can get when the surface tension varies from 10 to the minus 6 Newton per meter to 10 to the minus 9. And things are quite different. So that's the problem. So if I have this problem, the problem is how people try nonetheless to get information about that. So they try to use this lensing. That is, if you have a deformation, it means that you have a lens. And so if you look far, you are able to measure the focal distance, and then you are able to get the height, and from the height you can get So you have two kinds of experiments. Here they did it directly to get the surface tension in a so-called Windsor phases, which are quite small surface tension. And you have another example here where they use, as I told you, they consider the dynamics in order to get the viscosity. What is interesting is that you can go for very viscous system in a very short time, because you are not setting in movement all your fluid, but just a volume which is close to your beam waist. So since you are setting a volume which is around, let's say, 10 or 20 microns, then you can get information quite fast. I will show you that in a moment. So they try to increase this deformation by the lensing effect. So they use here pulses, nice pulses, laser pulses. But this is just to get intensity in order to get higher deformations. And of course, they try to measure the surface tension. And so, yes, they also try this experiment, but at least I have to mention them. They try to also measure some elasticity in viscoelastic gels. And for whom is interested, they also try to measure the tension of membranes. Because you have the feeling you have a membrane on a frame, and then you can shine a laser, and you can look at this kind of deformation at this size. So, We said nanometer resolution. Nanometer resolution means probably interferometry, and this is what we did. That is, we shine a drop with a pump laser, which is so-called in optics, in order to deform, and then we shine a probe laser, and we look at the interferences between some reference here on a lens, because I may use I may actuate this lens, but it could be the roof here if your liquid is transparent. But you can take any reference you want, and of course at the location of the deformation. And since you can take a reference anywhere you want, then you don't necessarily need to cross the film, and so it is quite adapted to opaque films or to rough substrates. And the setup is really like that, and so you have the pump beam here, the probe beam here, and we look at the fringe pattern between the reflection here and the reflection here. And here we have a glass prism, or it could be a wedge in order to remove the reflections. You know that when you are working in interferometry, you have to remove all the reflections. But this is exactly that. So, this is the kind of signal we can get, just to give you, because I will play with that. Okay. So this is your reference signal that you can get by actuating your lens, for instance, or as you will see later, if your drop evaporates. Imagine that your drop is evaporating, then what happens is you increase the path length, and so with time, and so you will have this interference signal in between this light and dark rings. And each time here, you will shine the laser, you will deform your interface, and you will get a deformation like, which are opposed like that, and we will analyze this deformation. What I have to say is this experiment is auto-calibrated, because we know that from the minimum to the maximum of a fringe pattern, we have lambda over 4n. So we know exactly this size. We don't have to try to calibrate in another way. You directly have the calibration. So here you have an experiment on glycerol. So glycerol is not evaporating. In fact, it's condensing water. So which is very interesting. Because, so you can condense just pico, I don't know, femtoliter and you may have this signal without actuating artificially a lens to get the same information. So you have your signal, so you extract it, and what you get is something like that. And what we wanted to see, if we change the waist, we change the signal, because we have a dependence in the bond number, so in the waist. And so we have the expression here to get here the final value, and you have this dependence, and you extract it quite easily to extract it because it's a fit, and we find data which are from the stationary value here and from the dynamic here and here. In fact, we have twice the dynamics to verify what we are doing, and we see that we can get data which are quite close to the literature. You may see some large errors or uncertainties, because I used to calculate errors in the way some old professor taught me 30 years ago. So I'm calculating serious errors and not what we see regularly in publication, which are not true. You agree with me? Yeah, the experimentalists probably agree with me. So then we look at something which is interesting. It's water, and we wanted to see this thin film effect. So what we do, so you will say, but water is inertial. It is not viscous, and you give us, yes, but if you start to have a thin film, this H-cube correction tells you that dissipation becomes huge, and then you can treat a very thin film of water as a viscous layer. Then the devil is in the detail, because how you can get very thin, no, I have to talk of that, very thin films that do not de-wet. It's an horrible question, because any prism right now have a coating, even if you don't ask it. So you have to remove it. And what I found is in the shelves of my thesis supervisor, I found very old prism that works perfectly. You have a spreading of the liquid. I don't know. And if one student break me this prism, we stop the experiment. So what you have to do if you have evaporation, you need a calibration. So it's quite easy. You count the fringe, and yeah, it is small because it is an inset, but you calibrate, in fact, the evaporation. You need to know the humidity in your room and so on, in order to get the height as a function of time. And then you have all these dynamics here. During time, what you do is you make an experiment here, and what you see, I didn't say that before, but this experiment is done in less than 200 milliseconds. So you can go to the dynamics as far as the dynamics of what you are looking is slower than your measurements. And by doing this, of course, you see slightly that the slope is different. I have to do that. So you can rescale these experiments by just measuring the time scale. You don't know what is the time scale, but you can measure it. And this is not theory. This is this experimental data. And then from that, you know that this time scale for thick films is independent of the height of the layer, and for thin films is dependent on the height. So what you do is you rescale your time scale here, let's say with the thick one, and you see this h cube dependence at very low thickness. Of course, we can get an analytical solution, and since we have a guy in our group who is specialist in BEM, he did it. And it works quite now, so we can see this film thickness dependence on water. Also, the devil is always that in the detail in this kind of experiments, because you need to have a nice atmosphere and so on, because if you have dust and things like that, it is quite bad. So now let's take, I have what? 5 minutes? So I have to go fast. So we look also at glycerol water. 3 minutes? My God. Okay. At water glycerol mixture, evaporating the interesting aspect is to evaporate the water, and then if you perform experiments at different time in your evaporation, you will get your time scale for an increasing concentration of glycerol. And so in this way, you are able to get the viscosity in one experiment done at different time. You are able to get the viscosity of your system as a function of. I can continue. No, I can continue. So you can do also that with latex suspension. So then you evaporate your water. So your concentration in particle is increasing. And of course, no. We were happy to find the Einstein law, and here you have huge error bars linked to the fact that in the calculation, the volume is involved, and the volume costs a lot. But in fact, it is quite nice. So 2 minutes now? Wow. So what about viscoelastic systems? So we try PAM solutions. So you have a typical deformation, elasticity, viscoelasticity, elasticity, viscoelasticity. So I have to go fast, but the idea is we took a 1D system because viscoelasticity with lasers starts to be very complicated. So we take a standard linear soft solid, and well, by using this, we can measure the strain, you can get the strain, and from this 1D equation, we can at least have an idea of the elasticity and the viscosities, which are, I would say, roughly, well, which seems to be in agreement with published data. I say it's simply because when people work with that, they never work at the same concentration, so we never know. But there is a tiny problem, is that when you look carefully, you see that the dynamic is dependent on the excitation. And this tells you that you are not necessarily in a linear regime, and if you also try to modulate inside your light window in order to have a frequency answer of your system, you see that you have also shear thinning. So it means, in fact, we need to go to such a complex law where power law variation of the viscosity as a function of the stress. This is what we're, well, okay. So this is what we are trying to do. It's difficult. It's difficult, but we're underway with Thomas Hales, for whom knows Thomas Hales. So I would like also to talk about 1 minute. 30 seconds on side effect. Well, in fact, radiation pressure is a toy for physicists in a lab, because any real liquid is absorbing. And if you absorb, what happens is that you have such a signal, and if you have such a signal where you see that it goes down like that, in fact, you have a coupling between radiation pressure like that, and since you are slightly heating your system, you have Marangoni effect, Marangoni deformation of your interface. Okay, and so the question is, we can measure this Marangoni effect. Okay, but this is almost my last slide. The idea behind that is, but okay, why should we continue to think in terms of transparent fluids while most of the fluids of interest are not transparent? And so now we are trying to set directly an Opto-Rheology based on Marangoni coupling. Why? Lasers are particularly interesting for that. What you want for Marangoni coupling is huge thermal gradient. This is exactly what we are able to do, because due to focusing, the size of the gradient is very small, and so you can use very weak overheating as compared to classical experiments. So this is the direction where we are going. And just to say you that, to come back to our first question about drying, I could tell you also things about coffee effect modified by lasers, where instead of having just this ring, you may control the concentration, and then you may control your printing on a substrate. And I thank you for your attention.
Long live India and France friendship.